Hello, my name is Owen Whitaker and this is my report for Lab 3, Circuits. The purpose of this lab is to examine and predict the behavior of circuits with capacitors, batteries, and resistors, both in series and parallel. We also want to become familiar with the measuring tactics used for conventional current and potential differences using multimeters. The fundamental physics principles that we will use throughout this lab include Kirchhoff's loop rule, which states that in a loop, the potential differences from one point all the way around to the same point will equal zero because of path independence. The node rule, which states that the current into a point must equal the current coming out of that point, and our two potential differences formulas for the resistors and capacitors. For a brief overview of the results, the current was equal before and after any resistors, confirming the node rule. Additionally, the potential differences in our loop added up to a bit more than 0 volts. However, this is because we did not consider any resistance from the wires, and the batteries may not have had exactly 1.5 volts of potential difference each. Lastly, we found that the light bulb with greater resistance took longer to charge and discharge than the bulb with less. For the first part of this experiment, the circuit was set up as shown below. We measured the current before and after the resistors, then reversed an ammeter connection, and then changed one of the ammeters with the voltmeter. Next, we measured the potential differences across the battery and both resistors using the voltmeter, summed this value, and compared with what we expected. We then compared ammeter readings when having a voltmeter across the 100 ohm resistor and an ammeter across the 100 ohm resistor. Lastly, we calculated the resistance for the listed circuit elements using potential difference over current. The initial conditions for this experiment were two 1.5 volt batteries, two resistors of 47 and 100 ohms, and two ammeters. The system with the circuit and the surroundings were everything else. We found that the current was the same before and after the resistors as 0.018 amperes, but that this value was a bit less than expected because our model calculation did not consider the resistance in the wires. When we reversed the ammeter connection, the sign of the potential difference became the opposite. When one ammeter was switched to a voltmeter, the measured volts were 3.0, and because voltmeters have a very high resistance, this pushed the current in the circuit very close to zero. The potential differences of the elements were measured as shown below. The total potential difference differed from following the loop rule by about 0.4 volts. However, this is likely due to us overestimating the electromotive force of the battery. When the voltmeter was placed across the 100 ohm resistor, the ammeter read 0.0169 amperes. This is similar to before because the voltmeter was attached in parallel, and because it has a very high resistance, very little current goes through it and the loop stays relatively the same. When an ammeter was placed across the resistor, the current read by the other ammeter increased greatly to about 0.06. Ammeters have very low resistance, and as a result, almost all of the current goes through the ammeter instead of the resistor. Therefore, because the overall resistance of the loop is about 1/3 the original, the new current is about 3 times the original. Lastly, we calculated the resistance using our measured values and confirmed that our resistors had similar resistance as we expected. And because we assumed the potential differences across the wires and ammeters are 0, these resistances were also 0. We set up the RC circuit using two 1.5 volt batteries, a 1 farad capacitor, and two light bulbs of 10 and 20 ohms. For each bulb, we connected the battery to the bulb and capacitor in series. While charging, we observed how the brightness changed and measured the time it took to dim out. We then removed the battery so that the only power source was the charged capacitor. With this, we observed how the brightness in the bulb changed and measured the time it took for the bulb to go out once again, and the capacitor to discharge. When the battery and uncharged capacitors were in the loop, the light bulb started off glowing and dissipated as the capacitor charged. The current decreased until the capacitor was fully charged and the bulb was off. When the battery was removed, the charged capacitor was the only power source in the circuit. The bulb started glowing, and as the capacitor discharged, the bulb became more dim until there was no charge and the bulb was off. At this point, the current was 0. The higher ohm bulb took longer to charge and discharge as seen by the time measurement listed, showing that the more resistance there is in a loop, the more time needed for a capacitor to change states. Although we could not make an actual round-trip potential graph since we did not measure the initial potential difference in the capacitor and how it changed throughout, we know that this model assumes the resistance is much less than it really is, and as a result, it expects the current to decay much faster than it actually does. Possible sources of error in this lab could include human error in data gathering methods and inaccuracies in the readings from the multimeters. In this lab, we assumed that the resistance in the wires and ammeters are 0 ohms and that the batteries were fully charged and produced exactly 1.5 volts each. If we charged the capacitor with no resistance in the circuit, the capacitor would charge instantaneously because the current in the loop would be approaching infinity amperes. However, something having 0 resistance is not possible. When we used an ammeter to measure how long it took to charge the capacitor and the battery to go dim with no artificial resistors, it took about 5 seconds, showing how even the wires, ammeter, and capacitor have some resistance. To conclude, we confirm the node rule that the current into a point always equals the current out of a point. While the potential difference throughout the loop was slightly greater than 0 volts, this is because we overestimated the positive electromotive force and neglected the negative potential differences from the wires and ammeters. Furthermore, because voltmeters have a very large resistance, they push the current to 0 in series since the resistance adds to the total, and they don't affect the current in parallel as the current follows its original path instead. Capacitors charge when they are not already fully charged and there's a power source, and they discharge when they have some charge and there's no power source. Lastly, the greater the resistance is in the circuit, the longer the capacitor takes to change states. Thank you.